All right, we're back into chapter 2, second PowerPoint, second video. So, if we have a cation, so we're in ionic compounds now. A cation is just a fancy name for a positive ion. Okay, so any ion that has a positive charge. Some examples, you can have a single element like magnesium. If it loses 2 electrons, it becomes the magnesium ion. And it has a magnesium, if it's in group 2 of the periodic table, those elements always form a +2 charge. So if I say the magnesium ion, I know that it's going to take the normal charge that it likes to have, which is +2. And then NH4 is one of the polyatomic ions that you're supposed to memorize. NH4 you should memorize as ammonium, not ammonia, but ammonium. And when you memorize ammonium, you should know not only that its formula is NH4, but its charge is also +1. Okay, so it has just a positive charge. The 1 is implied. All right, so those are a couple of examples. Then if we have a negatively charged ion, that's called an anion. An example, chlorine with a negative charge is called the chloride ion. Okay, now, when we make ionic compounds, the naming is going to be pretty similar to the covalent stuff, where the first element, like if I put magnesium and chlorine together, the first element is going to be the metal. It's going to be named normally, so that's magnesium. The second element, it's still going to get the IDE ending. So I'm going to go ahead and say, if I have Cl-, that's always going to be called the chloride ion. All right? And then we do have polyatomic ions. Most of the polyatomic ions are negatively charged. So SO4 is sulfate. Sulfate has a 2 negative or -2 charge, which we're supposed to memorize. But again, those are just some examples. So when we take positive ions and negative ions and put them together, if we put them together in the right ratio, that they're going to be attracted by the opposite charges attract. If we put them together in the right ratio so the charges cancel out, that's going to give us the formula of an ionic compound. Now, what are the charges? Well, this periodic table looks overwhelming at first, but it's really not that bad. We look for trends and patterns that we can use. The group 1 metals, alkali metals, are always +1. That's easy to remember, and we're going to use it over and over again, so it'll stick pretty quickly. Everything in group 2 is going to be +2. When you're in the transition metals, some weird things happen. So with those, we're not usually going to memorize them very much. And then when we get over to the non-metals, above the metalloid line, the noble gases don't make bonds, so we don't need to worry about them. The halogens always want to, like, basically when atoms react, they're always trying to get to be like the noble gases who think they're better than everybody else. Well, if somebody's really cool, then everybody else wants to be like them. So the halogens, they're 1 electron short of what the noble gases have. So when the halogens react, they're always trying to steal an electron from somebody else. So when they form a charge, if they steal an electron from somebody and bring it in, that's going to give them a negative charge. So the halogens always have a -1. Everything under oxygen, again, if they want to be like the noble gases, they have to steal 2 electrons. So if oxygen steals 2 electrons, then that makes him feel like neon. Sulfur steals 2 electrons, he's going to feel like argon. Okay? So -1 for group 7, -2 for group 6, -3 for group 5. Those are patterns that we notice. And then if I come back over here, like sodium is element number 11. If he wants to be like a noble gas, if he loses an electron, which when you lose an electron, you get a positive charge, that he goes from 11 electrons, he goes back to 10 like neon. So on both sides of the table, they're really trying to be like the noble gases. So that's going to make the charge of a lot of different elements to be very predictable. Specifically the elements that are over here and the elements that are over here. Those are the ones that are very predictable. Okay? Now, when you get out in the middle of the table, a lot of these elements they're too far away from the noble gases. They either have to gain a bunch of electrons or lose a bunch of electrons, so they usually can't do that. So transition metals, number one, they can't get to the noble gas electrons, so that makes it a little harder to predict. The other thing that happens is a lot of them actually have more than one charge. So, gold can be +1 or +3. Well, in a given compound, how do you know which one it is? And the answer is you don't really know unless somebody tells you. Okay, so when we get into naming compounds with the transition metals, there's going to be an extra step in the naming so that we can actually specify what the charge is. Okay, so the only ones you have to memorize are the ones that are predictable. The first two groups over on the left side of the table, the non-metals in the upper right, and then there are three more that you have to know. This diagonal box right here, these are very common metals that have a single charge. Silver is always +1. It's common, it's always +1, so you're going to have to memorize that silver is +1. Zinc is +2, always, and aluminum is +3. So there is a pattern, 1, 2, 3 for their charges. You need to memorize those, because when we start naming compounds that have all these elements in there, most of these are all going to use a Roman numeral as the charge or whatever, but on the ones that where we already know their charge, if you have memorized it like you're supposed to, we don't put Roman numerals on those. So basically, if you don't memorize those, you won't have any way to figure out what they are. Okay? So you need to know those two rows, you need to know these three elements, and you need to know your nonmetals. If you know those charges, then you're prepared for the next section. All right, so ionic compounds form through ionic bonding, which is where atoms exchange electrons. So the metals tend to lose electrons, the nonmetals tend to gain electrons. Once they exchange electrons, they become positively and negatively charged. Then they're attracted to each other, so they stick. And then that's my ionic compound. It tends to be metals and nonmetals, although when we get polyatomic ions involved, it doesn't always have to have a metal there. And then when we make an ionic compound, it's important that it always ends up neutral. Okay? So when we write a formula for ionic compound, it has to be the empirical formula, which is the lowest ratio possible. So if I'm combining magnesium and oxygen, I can't write MgO2. That's not right. Mg2O2, that's wrong. It needs to be MgO. 1 to 1, not 2 to 2. And then the formula weight, just like the molecular weight, is just going to be the sum of the weights in the empirical formula. So for magnesium oxide, this is the correct formula. I would look, magnesium's weight is 24.3. Again, I'm going to keep one decimal place because that one's not a whole number. Oxygen is pretty much 16. So 24.3 plus 16. The formula weight of magnesium oxide would be 40.3. All right, so if I start writing compounds and formulas, so I want to be able to predict if two elements are combined, what will the formula be? Now, I can't really do that with covalent compounds, because with covalent compounds, when they're sharing electrons, things get a little bit weirder. But with the ionic compound, the charges are usually predictable. So if I combine sodium and chlorine, if you look at the periodic table, sodium's in group 1, so I know that sodium is always going to be +1. So I'd write Na+. And then chlorine is in group 7. They're always -1, so it's Cl-. So when I put them together, what ratio would I put these two together to make it neutral? Well, if it's +1 and -1, if I just put them together, the charges cancel. So if the charges are equal, positive and negative, just put them together in a 1-to-1 ratio. So that formula would be NaCl. That's the correct formula of sodium chloride. Okay, so then it's like, well, what about sodium and oxygen? The next one. So again, sodium is always going to be +1. Oxygen is in group 6. It's going to be 2- or -2. So now, what ratio would I have to put them together? Well, basically, oxygen has twice as much charge as sodium does. So in order to cancel out, you're going to need 2 sodiums, each one a +1 and another +1, to cancel out a -2. Okay, so I could just, kind of picturing it, 2 of these guys can cancel out one of those. So then my formula is going to be Na, and then if I have 2 of something, I'm going to use a subscript to the right, Na2O. That's the formula of sodium oxide. Okay, now there is a shortcut there. Na plus and O2 minus. A lot of people learned in high school, if you take the charges, the charge on this one becomes the subscript over there, and then the charge on this one becomes the subscript down there. So the 2 goes on the sodium, the 1 goes on the oxygen. So again, that gives me my Na2O. The warning though, if you use that shortcut, make sure that when you get your answer that it can't be reduced. Okay, if it can be reduced, you got to reduce it down. So that might be an extra step. All right, so then the next one, aluminum and oxygen. So I have Al and O. So again, when I'm looking at this, I have to anticipate my charges. So aluminum is going to be +3 or 3+. Oxygen is going to be 2-. So what compound would they form? Well, I had to look for basically the lowest common multiple of the charges. With 3 and 2, the lowest common multiple of those two numbers is 6. So basically, if I had 2 aluminums, that's a total of +6. And if I had 3 oxygens, that's going to be a total of -6. That's the combination where the charges will cancel out. So my formula ought to be Al2O3. Now again, if I had done my shortcut, the 3 from aluminum goes down on the oxygen, the 2 from the oxygen goes down on the aluminum, Al2O3, I can get there another way. But again, just make sure you double check that it can't be reduced. Okay? So then finally, the last one on the slide, aluminum and nitrogen. So Al and N. And the question is, what compound will be formed between these two elements? Well, aluminum is always 3+, nitrogen always 3-. Again, when they're equal and opposite, I can just put them together. AlN, aluminum nitride. All right, so that's it. That's how we write our formulas of ionic compounds. So now we need to go through some of our naming rules. How do we name ionic compounds? Well, first of all, if I have an ion by itself, if it's a monoatomic cation, so monoatomic just means one atom. So like earlier I had magnesium with a +2 charge. All that I do is I just name the element, and sometimes, like in mastering chemistry, they might make you put the word ion after it. So Mg+2 is the magnesium ion. Okay, Ca2+ is the calcium ion. Okay, and if I have an anion, again a monoatomic anion, that's where I'm going to change the ending to IDE. So Cl- is the chloride ion. And then when we put them together, we're basically just going to name the two ions. So the first one, as we said before, is normal. The second one ends in IDE. And this time, we do not use prefixes. Now sometimes students get frustrated and like, well, why can't we put prefixes? Like if I have the compound MgCl2, a lot of students will say, okay, well that's magnesium, chlorine becomes chloride, so they'll say magnesium chloride, but then they'll say, but there's 2 chlorines, so they'll want to say magnesium dichloride. That's wrong. You cannot use prefixes with ionic compounds. And students are like, well, what's wrong with it? Well, to a chemist, it's redundant. It's unnecessary information that you should not have to put in there. Because if I know chemistry, I know that magnesium, like if you just say, hey, write the formula of magnesium chloride, if there's no di there, how would you know that there's 2 chlorines? And the answer is, well, I'm a chemist, and so magnesium, I know it has a 2+ charge. Chlorine, I know has a -1 charge. And so when I put them together, the 2 from that goes down, the 1 from that goes down, and it gives me the formula of MgCl2. So I don't need you to tell me with a prefix how many magnesiums and chlorines there are. I'm smart enough to figure it out myself. That's the attitude that a chemist would have. So when you name ionic compounds, you just name the metal, you name the non-metal with IDE, and that's it. Magnesium chloride, if you use prefixes, it's kind of like you're insulting somebody and saying, oh, you're not smart enough to figure this out yourself, so let me tell you, well, chemists don't like that. Okay? So that's our naming rules. So let's see. Now, if we're doing an ionic compound that only, like the metal only has one charge, then we're done. Like magnesium chloride, magnesium's always +2, it's very predictable, chlorine's -1, so everything's good. I can just name it magnesium chloride, and there's enough information there to figure it out. But if you remember the middle section of the periodic table, the transition metals and then underneath the metalloids, those metals often have multiple charges. So when you have one of those, you're going to have to use a transition metal. You have to use a Roman numeral to specify the charge. We saw that gold could be +1 or +3. You have to, when you name a compound, you have to tell somebody what Roman numeral it's going to be so that they can do it. So if I'm naming the ion, lead can actually be +2 or +4, either one. So if it's +2, and I want to tell you that, I would say it's lead 2, and it's a Roman numeral in parentheses. It's the lead 2 ion. If I had lead with a +4, then it's the lead 4 ion. And then when I name a compound, it's the exact same as before, but now I'm going to stick the Roman numeral in there. So I'm going to cut off the video. We'll practice it a little bit more in the next video.